Hello everyone. So now we will discuss part 3 of GOC, where we will discuss acidic and basic strength. So first we will discuss here types of acid and base theory. So we know that Arrhenius acid base theory and Bronsted-Lowry acid base theory and Lewis acid base theory. So Arrhenius acid base theory is what? Those substance which is H plus donor in water, they are called Arrhenius acids. Those bases which is in water giving OH minus, they are called Arrhenius base. Bronsted-Lowry means H plus donor. Bronsted base means H plus acceptor. Lewis acid means electron pair acceptor, electron deficient, and Lewis base are electron pair donor. Like here you can see that Ha is the weak acid, so it's forming H plus and A minus. So it's equilibrium constant, concentration of product divided by concentration of reactant. If that acid its acidic strength directly proportional to conjugate strength of conjugate base, means more the stable conjugate base, reaction will have tendency to move forward. Or if any electron withdrawing group is attached to this conjugate base, then this conjugate base will be more stable, then reaction will have more tendency to move forward, means acidic strength will be more. Or higher the value of Ka, concentration of H plus will be more, means reaction will proceed further, means acidic strength will be higher. You know Ka and pKa is inversely proportional because pKa is equal to minus log Ka. Similarly, here base is accepting proton forming conjugate acid. So this is Kb, product versus reactant. So product by reactant. So here basic strength is directly proportional to stability of conjugate acid. More the stable conjugate acid, more will be having tendency to move forward, means more will be basic strength. Or if that conjugate acid is attached to any electron donating group, so due to that electron donating group it will be more stable, then also basic strength will be more. Or directly proportional to Kb, higher the Kb value, means reaction will move forward, means more basic strength, means inversely proportional to pKb or directly proportional to Kb, because pKb is equal to minus log Kb. Next, if a strong acid is there, what is meaning of a strong acid? A strong acid means those acid which is unstable, highly reactive, so its acidic strength will be more. As acidic strength is more, means it will move from forward direction, means it will furnish more H plus. So always remember, a strong acid conjugate base is weak, or it's vice versa. If it is weak acid, so its conjugate base will be strong. Similarly, that a strong base is there, so a strong base means it will be unstable or its basic strength will be more. For a strong base, its conjugate acid will be weak or vice versa. Any reaction in this world always moves from unstable to stable, so that they will become more stable. So if a strong acid is there, so if it is unstable, means it will move further in forward direction and its dissociation will be more, means its alpha will be more, Ka value will be more, acidic strength will be more. Similarly for base, pH is equal to minus log concentration of H plus. Similarly, pOH is minus log OH minus. pKb is equal to minus log Ka, means higher the value of Ka, higher will be acidic strength, low will be pKa. pKb is equal to minus log Kb, means higher the value of Kb, more will be basic strength, less will be pKb. Now this is the most important. This acidic strength order is most important. You need to understand also and memorize. Like here you can see, if you remove one hydrogen, so this O minus is stabilized by this oxygen, resonating structure, identical resonating structure. So you remember from now onwards this order. So this is succinic acid is more stable than, means acidic strength is more than picric acid, means its conjugate base is more stable. then this conjugate base is more stable. So this is picric acid. After that, this is asquaric acid. Then after orthoparaphenol, orthopara nitro group. Then carboxylic acid. Then carbonic acid. Then both meta. Then one para, one ortho. Then after phenol. Then after water. Then after alcohol. Then next, second acidic strength order, like here you can see 1 comma 3 diketo. So like here this is more acidic site, this hydrogen is more acidic. So from here you, if you will take one hydrogen, so this conjugate base negative single double, negative single double, so this acidic strength is higher. Then after water, then after ROH, then after triple bond, means this hydrogen is acidic. Then after this, all those relatively very weak acids, NH3 and H2. They are not acid, in fact, they are base. Next, that some practice we will do, that conjugate base and conjugate acid. So if they are asking write conjugate base, means you just remove from here one H plus. So this is the conjugate base. Just you remove one H plus. This is the conjugate base. Just remove one H plus. So this is its conjugate base. Just remove one H plus, this is its conjugate base. Conjugate acid means you add one H plus. So here this is this conjugate acid. This is its relatively conjugate acid. This is you add in that one H plus, this is its conjugate acid. This is its conjugate acid. Clear? Now asking check the spontaneity, feasibility or delta G, whether greater or less than of this reaction. If delta G less than, then it is a spontaneous feasible reaction will occur. If it is greater than 0 delta G, or that if it is, then it will be non-spontaneous, it will be not feasible. So here you can see that check the spontaneity of the reaction. So here you can see carbon triple bond along with KOH. So this hydrogen is acidic hydrogen and this base, so it will form salt and water, but that we need to know whether this reaction is feasible or not. So for that, this order is very mandatory to keep in your mind. So you know that here triple bond is there and here water is there. So water is more reactive than triple bond. So water is as more reactive than triple bond. So water is here and triple bond is here. So you know reaction will move from a strong to weak, not from weak to a strong, because weak is unstable and a strong is unstable and weak is stable. So reaction will move from unstable to stable. So this reaction is not feasible. Whereas here you can see again triple bond and reacting with bicarbonates, carbonate and bicarbonates are base. So here it is forming salt and along with that acid. So this H2CO3 is relatively a strong acid compared to triple bond. How? You can see that triple bond, more triple bond and H2O is relatively stronger than triple bond. And with respect to H2O, you can see H2CO3 is stronger. Means can I say that H2CO3 will be more stronger than triple bond? So if H2CO3 is a stronger acid than triple bond, means again reaction is not feasible. Means this is a strong, this is weak. Now here this is succinic acid. So succinic acid rank 1 in acidic strength. So yes, this reaction will be feasible. Means this sodium will combine here, hydrogen will come here. So this is the weak acid compared to succinic acid. Similarly, not succinic acid, sulfonic acid. Next, moving further, you can see next this one sulfonic acid reacting with bicarbonates. Yes, here also it is feasible because sulfonic acid is more reactive than this H2CO3. Clear? Next, moving further, here this one is very important. Try to understand. Here as this reaction happening, so this is forming salt and H2CO3. So H2CO3 and this meta, you can see in this acidic strength, H2CO3 is here and just below that meta group is there, or after that this para, one para. So this all three having almost just relatively little bit more, means I can say this one is relatively more a stronger acid, but their acidic strengths are comparable, whereas here also it is comparable, even though its acidic strength is more, but they are comparable. So now try to understand only for this three, only for this three set, not for this one, not for this one, ortho one. So moving further, here you can see as this reaction, in this reaction, as meta reacting with bicarbonates, as meta reacting with bicarbonate, so it is forming H2CO3. So this one is relatively weak acid, this one is relatively a strong acid. So reaction will be in dynamic equilibrium because their acidic strengths are comparable, but overall if we'll see, it will having more tendency to go backward. But even though this reaction is feasible, why? Because as you know, H2CO3 is weak acid. At room temperature it will break down into H2O and CO2. CO2 gas will evolve. As CO2 gas will evolve, means this concentration will decrease, means reaction will having more tendency to move forward, because this reaction is in equilibrium, and according to Le-Chatelier's principle, if amount of product is decreases, means to again attain that equilibrium, reaction will move in forward direction. Hence, even though it is weak acid relatively, but due to that equilibrium nature, and as here CO2 releasing, so according to Le-Chatelier's principle, this reaction will move in forward direction to attain equilibrium. Hence, this reaction is feasible. Similarly, this same thing will happen for this para also. In para also, as here CO2 is releasing, so equilibrium disturbed. So to gain that equilibrium, reaction will having more tendency to move forward. But with respect to ortho, it will not happen because this is relatively very weak acid. So here it will form H2CO3. H2CO3 is a strong, so reaction not move from weak to a strong, reaction always move from a strong to weak. Clear? So this acidic strength is very mandatory. Without that you cannot do this, although just spontaneity and all. Next, coming to solubility. So solubility means interaction between solute and solvent. So more the interaction of solute and solvent, more will be solubility. So let's suppose here case study, this all those compounds are there, hydrocarbons, and in water, which of the compound will be soluble? So none of the compound will be soluble, even though you are seeing here that polar composition, that polar bonds and all, still it is insoluble. Still it is insoluble. Why? Because here you can see total 6 carbons are there. So these 6 carbons are hydrophobic part. So due to that water repelling group, so their interaction with solvent, it will be less. So here one case study illustration, you can see that methanol is highly soluble in water, infinite solubility. Similarly, ethanol also highly soluble. It's very important. Yes or no? Next, after that, 3 carbon. So as carbon increasing, hydrophobic part increasing, solubility you can see substantially decreased. If 4 carbon, it became 1.3 gram per ml. 5 and 6 to almost negligible solubility, means cannot dissolve. Means that compound with 5 or more than 5 carbon hydrophobic part is more. Due to that hydrophobic part, it is insoluble in water irrespective of any polar group. So yes, but one thing is that their salts are soluble in that water irrespective of all their hydrophobic, means this all those irrespective of their hydrophobic part, if you create their salt, means here if it is forming ONA, here also CH3C double bond O Na. So such type of compounds are soluble in water irrespective of their all those this hydrophobic part. Clear? So this two concept we discuss. One, that more or more than 5 carbon, that it is not soluble, but yes, even though even 100 carbon also will be there, but if it's salt, if it is forming, so that salt is soluble in water. So here that one question very famous, that separate this in IIT Advanced, till now they ask binary solution only, but we'll try to understand this quaternary mixture of solution is given and asking to separate them by acid base method. So suppose in this that phenol is there, toluene there, carboxylic acid there, and aniline there. So this asking to separate this one by acid base method. So in that, suppose this solvent, this is not soluble in water, so it is soluble in organic solvent such as ether. So in ether they are soluble. In that I am adding aqueous HCl. So as I am adding aqueous HCl, so HCl acid will react with which one? If it is reacting with this one, so what it will form? It will form here H plus, means it will form H2O plus and Cl minus, right? No, not possible. Here this one is also acid, this one is also acid, this one is not, this one is neutral. Here this one aniline is a base, so it will react with which one? You know na, that in acidic strength order phenol is also there, after that water is there, and then after alcohol in acidic strength. So this will not react with acid. So which one will react? This is also acid. Acid reaction not possible. So yes, this base will react with this acid. So when it is reacting, it will form NH3 plus and Cl minus, means it will form salt, anilinium salt, anilinium chloride. So this anilinium chloride, you know that salt of any that hydrophobic, irrespective of hydrophobic part, it is soluble in water. So here it is soluble in water, and ether is, since ether mass is more, so ether will be here. In ether, these three compounds are there, and this compound is soluble in water, upper layer. Now we can segregate this one by separating phenol and all, and after that getting this anilinium chloride, if will react with NaOH, so what will happen? NaCl, and from here water will release, again you will get aniline. Now this, from quaternary it became tertiary mixture. Now this tertiary mixture we are reacting with NaHCO3, bicarbonate. So by reacting with bicarbonate, now here two acids are there. In that, you know, if phenol will react, so it will form H2CO3, and H2CO3 is more a strong acid as compared to phenol, means that reaction is not feasible. So if NaHCO3 is reacting with carboxylic acid, then it will form H2CO3, and H2CO3 is relatively, as this one we are reacting with carboxylic acid. So carboxylic acid, as it will react, so it will form CH3CONa and H2CO3. H2CO3 is relatively weak acid as compared to carboxylic acid, means reaction is feasible, means now this will be soluble in water. Again we can separate and we can react with any H plus source, so it will be that your benzoic acid will be recovered. Now this two substance is there, so this two substance, in that if will react with base, so only one acid is there, so it will form ONA, and along with that H2O will be formed. So you know that phenol is more reactive than water, so yes, that will be segregated, and by this we segregated quaternary mixture by using acid base reaction. Using the concept of that acidic strength, we segregated all four compounds in separate container. Clear? Next, moving further, acidic strength directly proportional to, next, acidic strength you can see directly proportional to stability of conjugate base. Stability of conjugate base. More the stable conjugate base, acidic strength will be higher. Or electron withdrawing group, if it is present to conjugate base, then also it will be acidic strength will be higher. These factors are common factor. Left to right, what will happen? Electronegativity is increasing. Top to bottom, size factor we will study. In case of strain, less the strain, that species will be more stable. In case of hybridization, percentage of S character, if it is more, means that conjugate base will be more stable, like that. So like here you can see HF is there, HCl, HBr, HI. So you know that HI bond is relatively weak, so its bond strength is less. So bond strength is less, so it will break down easily, means its acidic strength is high, easily it can furnish H plus. And iodine conjugate base size is big, so big on bigger size, overall -1 charge density is less, so charge density is less, so overall it is more stable. So charge density on I minus is less, so relatively it is more stable. So that only, as we are moving left to top to bottom, size increases, more the size, so due to that charge density on that less, and charge density is less, so that conjugate base is relatively more stable. So stability of conjugate base more means acidic strength more. If we are coming top to bottom, so top to bottom, sorry, left to right, so left to right, if we are moving electronegativity, which one is more electronegativity? Fluorine. So fluorine, if it is, so as you can see, its conjugate base for any substance, if it is asking acidic strength, means you first form its conjugate base, and if conjugate base is more stable, then acidic strength is more. So here its conjugate base is fluorine. You can see fluorine is more. So always left to right, always all those answer we will give by electronegativity, and top to bottom always answer we will compare by size factor. There could be many other factors also, ionization energy, this and that, but always we will give result by size factor, and left to right by electronegativity. Clear? So this is left to right. So here you can see fluorine is more electronegative. So if it is more electronegative, on that if negative charge is coming, okay, appreciable. Oxygen is relatively less electronegative, so on that oxygen if negative charge is there, and fluorine having negative charge, since fluorine is more electronegative, so they can digest that negative, means I can say it is more stable, right? Because its tendency, its nature only to having more negative charge, because its electronegativity is more, so they can sustain that negative charge, means it is relatively more stable. Next, here you can see that triple bond, so percentage of S character is more, so more the percentage of S character, conjugate base will be more stable, because its nature only more electronegative, so they can sustain that negative charge. Whereas here percentage of S character relatively less, here very less. So which one is more acidic? This one, because its conjugate base is more stable. Clear? Similarly here CF3 and CHF3, CHCl3. So its conjugate base will be what? CF3 minus, and here CCl3 minus. So carbon having negative charge, and carbon sorry, so here carbon having negative charge, and here chlorine is there, so chlorine having that vacant d orbital, so due to that it will be more stable as compared to fluorine only through minus I it is stable. Clear? Next, moving further, coming back here, so these are the three species given, so its conjugate base, draw its conjugate base and conjugate base. So always first we will see a stability by which one we discuss, so that sigma resonance, after that quasi aromatic, after that aromatic, then resonance, then hyperconjugation, then inductive. So here it is negative, so it becoming aromatic is more stable than non-aromatic and normal. So this is more acidic because its conjugate base is more stable, so it is more acidic strength having, then after this, then after this. Clear? Again you can see here it having negative charge, conjugate base, more the stable conjugate base, more will be acidic strength. So here negative charge, sulfur having vacant d orbital, minus r, means here it is back bonding more stable, here also back bonding more stable. Here oxygen will have minus I, but sulfur having that minus r, so due to that back bonding it is more stable, but here only minus I. So here that resonance effect is prominent, So this conjugate base will be more stable, means its acidic strength will be more as compared to this and this. Clear? Now for this compound you can see that acidic strength for position 1, 2 and 3. So for 1 conjugate base will be here, right? For 2 conjugate base 1 hydrogen remove this, and for 3 hydrogen is removed, conjugate base will be here. So for this negative single double, so it will have 6 resonating structure. 1, then after here 2, you see bridgehead. So from here 3, 4 and 1, 5, 6. Right? So it having 6 resonating structure. It having 0 resonating. Why? Negative single single, negative single single. So it having 0 resonating structure, whereas it having 4 resonating. So more the resonating structure, more the stability. Means 1, then after 2, then after 3, because 2 having 4 resonating, 3 having 0 resonating. Clear? Next, moving further. No, 3 having more, no? So 3 having more, 2 having 0. So we can little bit correct this one. Instead of 3, 2, we can keep it here 3. And then after 2, because 2 having 0 resonating. Next, moving further, we will discuss this compound. Again here you can see position 1, 2, 3. So here conjugate base, so negative, you know that this is the bridgehead. So bridgehead is not non-planar, so resonance will not happen. Negative single double. So here 0 resonating structure. Here also 0 resonating structure. Here it will have, because negative single double. So here it can do conjugation. So second position is stable. So it is more acidic. 1 and 3 cannot do resonance. Even though here to negative, after that negative single single. So already no that conjugation only not there. Even conjugation also if it is there, it cannot do resonance. Clear? Because for conjugation system must be planar. This is not, bridgehead is not planar, Brett's rule. So here that negative charge is there, here also negative charge, but you can see here that carbon will give plus I effect, whereas here this negative charge is balance, means more stabilized by minus I effect. So one is more stable, means its acidic strength is more. So which one is more? First, second due to conjugation, then after first due to minus I effect, and third one is at last because it having plus I effect. Clear? Next, acidic strength of this two compound. So you can see carboxylic acid. So here O minus. So it having identical resonating structure, conjugate base. But this is not identical. Always remember, identical resonating structures are quality resonating structure, and it is more stable. So this one. Next, coming to this oxalic acid, Ohm's gap. Yes or no? So this is oxalic acid. Then after malonic acid, and this is succinic acid. So here you can see this one is no conjugation is not there. So overall this is having withdrawing tendency. So this is minus I group. Here this one also minus I. Here also this one minus I. But as distance increases, minus I effect will be less. So this conjugate base will be more stabilized by this minus I. So acidic strength is more. Next coming, if suppose if before that only it is CH3 C double bond OO minus, and here again you are forming its conjugate base, so it will be also minus. So already it was having minus charge, means it will decrease its negative charge by giving electron, means it is behaving like a plus I. So here conjugate base will be less stable. As here distance relatively increases, so this will be relatively more stable conjugate base. As here distance more increase, so it will give electron but not that effective, means here what it will be, this conjugate base will be relatively more stable. Clear? Now this one you know that malic acid and fumaric acid. So malic and fumaric, as here if you will do, it's one conjugate base cannot do hydrogen bonding, but here it's one conjugate base, negative, C double bond O minus can do hydrogen bonding, means this is relatively stable. Clear? So this is more stable because its conjugate base is more stable due to intra hydrogen bonding, hence its acidic strength is more. Similarly, coming back to this compound, you can see that calculate the oxidation, that acidic strength of this aldose. So in that, first having 3 resonating structure negative, so 1 2 3. Second having 5 resonating structure, third having 0 resonating structure, and fourth having 8 resonating structure. So more the resonating structure, more the stable conjugate base, more the stable conjugate base, more will be acidic strength. Such type of questions in class we discuss, and even though you know that very simple that here it will be negative, so with that respect how many resonating structures will be there, already I discussed in part 1. Next, moving further, here you can see phenol and thiol. So here that phenoxide ion and here S minus. So S minus can give also electron and S minus can take also electron from phenyl, means benzene system, due to its vacant d orbital. So it will having double resonating structure. So more the resonating structure, more the stable conjugate base, more will be acidic strength. Now here this one is very important, formic acid and normal carboxylic acid, and this one benzoic acid. So in benzoic acid what will happen, that generally that we will think that here this is the conjugate base and this conjugate base having identical resonating structure. Yes, it is there, but one is possibility that this negative, you can see negative single, double. So here that negatives this one like this as it is forming, and here this one, so here double bond will come, right? So due to that what will happen, this aromatic will break. As aromatic will break, that conjugate base will be very unstable, or that resonating structure is very unstable, and due to that overall its resonance hybrid will be unstable. As its resonance hybrid will be unstable, acidic strength will be less. Are you understanding? That since here one it can do identical resonating structure, no problem, that everyone is doing its identical resonating structure. Along with identical resonating structure, this negative is moving here. So here this bond will break. There is one possibility, means carbon, this will become double bond. Here negative charge will come and this oxygen will become double bond. Means here aromaticity is loosed. That resonating structure is very unstable. Due to that overall its resonance hybrid will be also affected by that. Means such type of phenomena should not happen. This aromatic compound must be maintained, because we know aromatic is more stable than non-aromatic. So here if we will do any ortho-substituted, due to that what will happen, Sir effect will happen and it will rotate. As it will rotate, means it will become non-planar, means that double bond C double bond O and O minus will be perpendicular to the plane, perpendicular to benzene ring, means now it will not do resonance with plane, that benzene ring, means aromaticity will be maintained. So that only here you can see ortho-substituted, that carboxylic acid are more acidic, and that is only called ortho effect. So ortho-substituted carboxylic acid, since it became perpendicular due to Sir effect, now aromaticity will be not disturbed, so resonating hybrid will be more stable due to identical resonating structure, hence its acidic strength is more as compared to those which is not ortho-substituted. Clear? So here you can see that in this compound, that here this carboxylic acid is there 1, this is 2 and this is 3. So here due to that ortho-substituted, this one will rotate. So it will be perpendicular to the benzene system. As perpendicular to the benzene system means now this aromaticity will be maintained, means acidic strength is more. Here also with respect to this you can see it is ortho substituted. So here 2 ortho substituted. So relatively we can say more acidic strength. Then after here and here at last, because due to that aromaticity will disturb. One possibility is there. So which one is the answer? Third, then second, at last first. Clear? Now here you can see that we have to tell that which one having highest acidic strength. So here you can take its conjugate base. So if we'll take here that conjugate base, so that conjugate base, then it will be negative. So negative single double, it can do conjugation. But if we'll do here, due to that flipping, since this is flipping, this is not joined, so it can flip also. So due to that flipping, its resonance will be not that effective, means negative single double will be not that effective, as here it is interlocked. So here that delocalization can happen proper, means its acidic strength is more. Clear? So acidic strength we completed. Now we will discuss basic strength. So for basic strength also, more the stable conjugate base, more will be basic strength. Clear? So here you can see that this is the all those F minus Cl minus Br minus I minus is given. So you draw its conjugate acid, you draw its conjugate, you write its conjugate acid. More the stable conjugate acid, more will be basic strength. Once again, more the stable conjugate acid, more will be basic strength of I minus or HF. So like that. Here you can see which one is more stable. HF is more stable. Why? Because hydrogen is 1s, fluorine is 2p. So 1s 2p overlapping, whereas this is 1s 5p. So this bond is relatively stronger. So this conjugate acid is more stable, means this basic strength is more. Now in basic strength mainly we have to study that amines. So for amines always you apply this Brahmastra, that aliphatic amine is more basic than aromatic amine. Aliphatic amine is more basic than aromatic amine. Why? Because in aromatic amine that amine lone pair will get delocalized, but in aliphatic it won't get delocalized. So more the lone pair, its tendency to accept H plus will be more, means basic strength will be more. So aliphatic amines basic strength is more than aromatic amine. Localize next, all those rules you have to apply in sequence. So next, localized electron density is more than delocalized electron density or delocalized lone pair. If this two rule is null and void, then that whatever that amines are given, first you write its conjugate acid and conjugate acid acidic strength you compare. So more the conjugate acid acidic strength, understood? So here that more will be its basic strength. So conjugate acid, first we will see that conjugate acid strength we will see, means stability, not strength, stability. So we will see by resonance. So if first rule is null and void, second rule is null and void, then that base you derive its conjugate acid by adding H plus and its strength by resonance. If it is more stable by resonance, then yes, that basic strength will be more. Through hybridization, sp3 is more stabilized than sp2 and sp2 is more stable than sp, conjugate acid. And then after solvation effect, we will see here. And last, electron donating group, if it is there in conjugate acid, if electron donating group is present, means conjugate acid strength will be more. If conjugate acid strength will be more, or like that also we can see, no problem. Just that if that in amine system electron donating group is present, means they are giving more electron to amine system, means they are having more electron density, means more basic strength. And then after electron withdrawing group. So once again, aliphatic is more over than aromatic amine. Then after localized electron density is more, having basic strength than delocalized electron density of amine. If these two are null and void, then you write its conjugate acid and then you check its conjugate acid strength, not strength, stability. So through resonance, if it is stabilized, well and good. If it is this one is null and void, then you go by hybridization. sp3 means percentage of s character will be less. So if percentage of s character will be less, then that positive charge is more stable. Correct? After that, sp2 and sp having percentage of s character 50%, means that positive charge will, if positive charge is coming on 50% s character, then that will be less stable. After that, solvation effect. And last, if electron donating group is present in that amine system, then it will have more than the electron withdrawing. What is the solvation effect? Like Sir effect or ortho effect, solvation effect is also there. So solvation is like if aniline primary amine only, on that if ortho-substituted bulky group if will be there, then it will have very less possibility to accept H plus because of hindrance, because this bulky groups are already there. So very difficult to accept H plus from other entities. Means it's that ortho-substituted in aniline group is stopping it to accept H plus, means decreasing its basic strength. So due to this, it is called SIP, steric inhibition of protonation. Means ortho-substituted aniline system having less tendency to accept H plus, and this phenomena is called steric inhibition of protonation. Means its basicity is very negligible. Clear? So if one ortho-substituted is there, so its basic strength is very less. If it is at meta, so somehow it is withdrawing the electron. Here you can see it is giving electron through. Here it is giving electron through plus I. Here it is giving electron through plus H, and plus H is ortho and para derivative. So here electron density is increasing. So due to that, this is also getting electron density through this plus H. So here its basic strength is more. So this one is electron donating. So here we can apply that rule. First, that you can see this is a delocalized lone pair. This one is also delocalized. This one is also delocalized. First one is what? First one is your aliphatic, then aromatic. So here all are here your aromatic only. This all three are aromatic. Then after delocalized versus localized. So here this is also delocalized, connected with conjugated system. This is also. Next one is that after that we will make its conjugate acid. So conjugate acid, this one NH3 plus, NH3 plus, NH3 plus. Then after we will see through resonance. So resonance not happening. Then after we will see through hybridization. So hybridization also. This is also sp3, this is also sp3, this is also sp3. Then we will see through solvation effect. So solvation effect, this one is the last. After that, fourth, last one is that electron donating and electron withdrawing. So electron donating is more. So here both are electron donating, in that this one is donating by plus I, whereas this one is donating by plus H. And plus H is electron is reaching here effectively, because plus H is ortho and para derivative. So here electron density is more, means its basic strength is more. Means all questions of amine, if we are applying that Brahmastra in sequence, always we will get the correct answer. Next, moving further, here you can see that all those are conjugate base. So basic strength will be higher for which one? That carbon is less electronegative, so its tendency to give lone pair will be more. Whereas fluorine is more electronegative, so its tendency to give its nucleophilicity is less, its basic strength is less. So basic strength is higher for carbon. So if you are moving left to right, always you will decide by electronegativity. So here as we are moving left to right, fluorine is more electronegative, so its basic strength is less. Whereas this one is less electronegative, so its tendency to give its negative charge or lone pair is more, its basic strength is more. Clear? Similarly here, this all those are conjugate base. In that, this one is sp3, so sp3 will give electron, whereas sp2 and sp are percentage of s character relatively more, so they will withdraw the electron. So here charge density relatively decreases, but here charge density is more, means its basic strength is more. Clear? Next, coming to here, you can see this one is delocalized, this one also delocalized, this one also delocalized, this one localized. So here this one is localized, this one localized, this one localized, but this one localized, in that electron density is coming more from this two group. Here electron density is relatively less coming, so overall basic strength is here, because here it having more electron density than after here and then after here. Clear? Here you can see what happening, SIP. So here SIP happen, here more SIP happen, here SIP not happen. So basic strength were higher, here it will be higher, then after here and here at last. So third having more, then after one, then after two. Clear? Next, moving here, you can see this is not amine, this is N, N dimethyl. So this is for this, if suppose here it is there, so this is SIR effect, this is not SIP. So as it will rotate, so due to that now it became delocalized. Localized lone pair. As localized lone pair, so its basic strength is more, because localized is more than delocalized. Correct? So this one, now remaining all are delocalized, because here this electron will move from high to low, here also high to low, here also high to low. Here this is giving electron through plus H. So somewhat that here it is giving through plus H. So then after 1, then after 2, and then after 4. Clear? Next, moving further, in this question you can see that here this one is delocalized, here also this one delocalized, and this is localized. This one is aromatic, this one is aromatic, this is aliphatic. So first rule is aliphatic is more than aromatic, then after localized is greater than delocalized. So aliphatic is greater than aromatics, and aromatic in that this one is localized, here this both are delocalized. So 1, then after 2. Clear? Next, here you can see this lone pair is localized lone pair, here this one is delocalized, here also delocalized. So localized is more, means 1, then after this is delocalized. It can delocalize in one direction, but here delocalization is possible in both direction. Correct? So 1, 2, 3. Next, here you can see basic strength of nitrogen. Here this is also localized, this one is also localized, but as this will give, so here flipping may happen. Flipping means it can change that side also. So due to that, its giving tendency will be less, because as it is going that side, so that it will be not that effective, means it is creating hindrance, but as it is here interlocked, means now it can easily give its lone pair to H plus, means basic strength is more. This is only called amine flipping. Clear? Now here you can see this, all those in that which one is more stable, this one is the more stable, 6-membered. So 6-membered more stable, so it can give easily its lone pair. This one is relatively unstable, so it cannot give, and then after, means here its conjugate acid is relatively more stable, its conjugate acid is relatively less stable, and this one is very less stable. So this conjugate acid is more stable, means its acidic strength is more. Clear? Next, moving further, you can see this. In this compound, this nitrogen is localized. This one is also localized. And this is sp2. sp2 means bond will be formed at 120 degree. So already this bond is at 120. So another, as I am making its conjugate acid. So conjugate acid means that bond will come here, right? And that bond will do hydrogen bonding with this. So due to that chelation, 5-membered ring, it is more stable. Clear? Similarly, here you can see, here also that this one is already 120. Another bond also will be at 120, means hydrogen bond will come here. Yes or no? And that hydrogen bond will do chelation with this. So that is relatively more stable. But here you can see it will rotate. Even chelation will happen, but this sigma bond will rotate. So due to that, this chelation is not that effective. But here this cannot rotate here. So this chelation is more stable. So hydrogen bond will be formed like this only. Hydrogen bond you cannot create anywhere like that. So hydrogen bond, since it is sp2, so it will come like that 120 degree angle, and it is forming chelation, and this chelation cannot do conformer. So this is more stable, means this conjugate acid is more stable as compared to this. Here you can see 120 degree means here. Now it cannot form hydrogen bonding with this one like this. Clear? So here hydrogen bonding cannot happen. Why hydrogen bonding cannot happen? Because its bond should come this way, 120 degree sp2, and its bond should come 120 like this. Whereas here its 120 was coming like this, and its 120 angle was coming like this. But here this both are becoming parallel, so chelation only cannot happen. So here chelation and no rotation. So this conjugate acid is more stable. Acidic strength of this compound is more as compared to this, and at last this one. Clear? Next, this one is the most important, that ammonia, primary amine, secondary amine, and tertiary amine. If it is there in aqueous medium, already we discussed that all those, it's how it is happening, and that all those, that result. But here we have to only in synopsis we need to remember its result. So remember SPTA, that first secondary amine, then after primary amine, then after tertiary amine, after that ammonia, that is the basic strength. In gaseous phase, tertiary, then secondary, then primary amine, then after ammonia. Clear? And this is valid when it is CH3 methyl group. Instead of methyl, if it is ethyl group, then this tertiary amine, one step it will come forward, means it will be STPA. If instead of ethyl, if we'll keep here propyl, then again tertiary will come one step forward, means it will be tertiary, secondary, primary amine, and it will be equivalent to gaseous phase. Here it is in aqueous phase, and this one is in gaseous phase. So at propyl, after that butyl, whatever you will do, its order will be same like gaseous state. Clear? Next, here you can see that basic strength. So already we discussed basic strength will be higher for this one, because it cannot rotate, whereas here chelation will happen but it can rotate. Here so chelation only cannot happen. This guanidine base, so here you can see Kb value is given. So higher the Kb value, less will be its K. Higher the pKb value, less will be, higher the pKb value, less will be Kb value, less will be basic strength. So this is the more basic. Then after this one, so this guanidine base series you need to remember. So if suppose they are attaching these questions also along with that ammonia amine questions, so you can apply that Brahmastra. Along with that Brahmastra, keep this guanidine base also in your mind. Like acidic strength order you remembered, like that little bit this one also you try to remember. Okay, here also you can apply Brahmastra. Somewhat it will be valid, but More precisely we need to remember, then only we'll get the answer. Now coming to resonance energy. So resonance energy is what? That difference between that resonance hybrid and most contributing resonating structure, means it will be relatively more stable. In between the energy difference is called resonance energy. So resonance energy directly proportional to extent of resonance. More the resonance happening, more the delocalization of electron will happen, and more the delocalization of electron, more the energy will release, and that energy is only resonance energy. Number of resonating structure more, then also resonance energy is more. More the stable compound is formed, then also resonance energy will be more. Resonance energy can be estimated, cannot be calculated 100% accurately. Resonance energy is shown with negative sign because energy will release, because delocalization of electron happening, so due to that energy will always release. Resonance energy can be estimated by different processes. Resonance energy can be calculated by that, you can see here, by heat of hydrogenation. Heat of combustion we studied. Heat of combustion directly proportional to number of carbon, and second, if carbon atom is same, then inversely proportional to stability or directly proportional to strain. Here we are discussing heat of hydrogenation. So resonance energy also can be calculated by heat of hydrogenation. There are many several processes by which we can estimate heat of hydrogenation, resonance energy. In that, one method is heat of hydrogenation. So resonance energy is calculated that enthalpy of experiment minus enthalpy observed. Okay. So whatever the value experimentally coming minus observed value, that will be resonance energy. Like here you can see that one bond we are breaking and adding H hydrogen bond through syn addition using nickel or platinum metal. So here that hydrogenation happen, so energy is released since we are breaking one pi bond and forming two sigma bond. So sigma bonds are strong, so energy will release more, as energy giving we are less. So overall enthalpy will be minus 29 kilocalorie per mole. Since here we are breaking two bonds, so 29 into 2 minus 58. So experimentally also minus 58 and observe also minus 58. So overall resonance energy is here 0. And of course here you can see resonance not happening, no delocalization because conjugation is not there. Double, single, single, double. But here as you can see conjugation is there. Since we are breaking same two double bond, so expected is minus 58, but in reality observed is releasing minus 55. So resonance energy is that expected minus observed enthalpy. So overall resonance energy is coming minus 3 kilocalorie. So due to that conjugation, how much energy is released? Minus 3 kilocalorie. Now here heat of hydrogenation, so you can see overall this system in conjugation. So expected is minus 29 for one pi bond. So minus 29 into 3 minus 87. But in observe it is coming minus 51. So resonance energy is minus 36 kilocalorie. Means we can say that more the conjugation, more the resonance energy. So in case of larger conjugation, resonance energy also will be more. So here you can see resonance energy, here only two resonating structure, but here more resonating structures. So more resonating structures means more resonance means more resonating energy. Next, moving further, here you can see that here it having only two resonating structure, but here it can have that chlorine can give also, chlorine can take also. So here since this fluorine is giving effective that 2p, so back bonding is more effective as compared to 2p 3p. So here we will see more about quality over quantity. So one is more than two. Next, after that, here you can see nitrogen high electron density to low electron density, it is in conjugation. Here also it is in conjugation, here also in conjugation. So nitrogen, oxygen, sulfur all will have how many resonating structure? that is same only, but along with that sulfur can take also this pi electron. So overall it will have 10 resonating. So more the resonating structure, it will be more resonance energy. Similarly here you can see this is the cross, whereas this one is extended. So both are analogous series, extended having more resonance energy than cross. Clear? Now here you can see due to Sir effect, this will be perpendicular. So here resonance will be relatively less, but here relatively this lone pair also part of conjugation. So here resonance energy is more. Clear? Here you can see this one is positive single double, positive single double. Here also positive single double, means both are same only. So for same resonating structure, resonance energy also will be same. At last we will discuss bond length, bond strength, bond energy and bond order. So bond length we know, bond strength also we know, bond energy also we know. While breaking the bond, for 1 mole whatever energy we are giving, that is called its bond energy, or whatever the energy released for the formation of 1 mole of that entities or that bond, that is called bond energy. So either it can be endo or it can be exo also. Like here you can see that one example, like here, here. As you are breaking this bond, so here as you are giving energy, or suppose reverse of that, if you are forming this double bond, so in that energy will be released. Means formation of bond is exothermic, breaking of bond is endothermic. So here as we can see that bond length is directly proportional to extent of resonance. More the resonance, so more will be bond length. When initially it is double bond. When it is initially double bond, so due to that resonance it will be next time single bond. So overall bond length will be increased. Or it is inversely proportional to extent of resonance. When it is initially single bond, next time due to conjugation it will be double bond, means bond length will subsequently decrease. Bond length inversely proportional to bond strength, inversely proportional to bond energy, and inversely proportional to bond rotational energy barrier. More the bond rotational energy barrier, means bond order is more, bond length is less. So moving further, here you can see that bond length. So here bond length is 1 only. Here due to conjugation bond length is more than 1. Here also due to conjugation bond length is relatively more. Here you can see due to conjugation bond length will be again relatively more. So bond order will be relatively more. So if bond order is here more, bond length will be less. Here conjugation relatively less, so bond order will be relatively less, bond length will be relatively more. Here you can see conjugation only 1, so here bond order will be relatively less, bond length will be relatively more. So which one is bond length is higher? 1, then after 2, then after 3, then after 4. Clear? Here you can see both X and Y bond length will be here positive. So bond length will be same only because double single positive. So overall resonance hybrid, in that bond length will be same. Similarly here you can see that X and Y is there. So X is double bond order, means 2 bonds are there. Here only 1 bond is there. If we will add here H plus, so by adding H plus, what it will be? By adding here H plus, not H plus, like suppose here we are breaking this one, like this lone pair is here and this bond is breaking. So it became O negative and here it became OH positive double bond. But since you know oxygen having plus charge is coming, plus charge on oxygen is more electronegative atom, on that positive charge is unstable, means this resonating structure is not favorable, means overall this bond length will be relatively, that bond order will be 1 only, and this one bond order will be relatively 2 only. Means can I say here bond order is less, means bond length will be more. So here bond length will be more, means Y is greater than X. Here again, due to conjugation, this all are same only, so bond length will be X is equal to Y is equal to Z. Or another way, not same, we can see that here, that due to cross, if electrons are moving, because both are pi pi, so let's suppose electrons are moving this direction, means here electron density is more, means bond order is more, means bond length will be less. Or another possibility, it can move this side also, means this bond order will be less, means bond length will be more, means I can say Y will be greater than X and Z, XZ will be equal, or Y will be less than X and Z, XZ will be equal. Now this is asquaric acid. Asquaric acid, this is the conjugate base. So asquaric acid conjugate base, in that you can see its resonating hybrid is coming this one. So in that, this all those bond order is same, here this bond order is same, means I can say bond length of these bonds are, means X is equal to Y is equal to Z is equal to W, and bond length of PQRS will be same. So already in class we discussed its resonating structure. So through resonating structure, this is its resonance hybrid. So remember, this all bond length are same, and here this bond length are same. Clear? Next, moving further, bond energy also calculated by stability of free radicals. So more the stable order of free radical, bond energy will be relatively less. So here you can see this is 1 degree free radical, here it is 2 degree free radical, and this is 3 degree free radical, and this is 2 degree. So 3 degree is more stable than 2 degree, and 2 degree is more stable than 1 degree. So 3 degree, since it is more stable, so its bond energy is less. So 2 will be that stability order, since its energy is bond energy will be, so here stability order 3, so 3 bond energy will be less, and 1 stability order is minimum, so bond energy will be maximum. Clear? On behalf of this question is there. Last, heat of hydrogenation. So heat of hydrogenation, like that only, that 1 mole of compound added with H2 molecule, then it becomes saturated compound, that is called heat of hydrogenation. So enthalpy change when 1 mole of any compound is completely reduced. So this is after complete reduction. This is syn addition, you know. So in that, energy how much is releasing? Minus 29 kilocalorie, because we are breaking 1 sigma bond and breaking 1 pi bond and forming 2 sigma bond. So here what will be? Heat of hydrogenation is directly proportional to number of pi bonds. More the number of pi bonds, more will be heat of hydrogenation. But this is valid when that all those given compounds, either it is aromatic or none is aromatic, then only we will apply this one. If some is aromatic, some is non-aromatic, then we will not apply this number of pi bonds concept. So pi bonds only we will apply, more the number of pi bonds. If none is aromatic or all is aromatic, then only. Or inverse, second, if this is null and void, if pi bond is same, then we will go by stability. More the stable, less will be its heat of hydrogenation. And this is exothermic only, because we are breaking 1 pi and forming 2 sigma. Clear? So this is all about. So this is exothermic. So on behalf of this, we'll do some questions. So here you can see that it having how many? That 2 alpha hydrogen. Here how many pi bonds? 2 pi bonds. So more the number of pi bonds, all are non-aromatic. So here more the number of pi bonds, it heat of hydrogenation is more. So first 2, then after here it having how many? 2 alpha hydrogen. Here it having 6 alpha hydrogen. So this alkene is more stable, so its heat of hydrogenation will be less. So second, then after first, then after third. then after third. Next, moving further, now here you can see that here how many, that one pi bond, here also one pi bond, but here it having how many, 3 4 ja 12, correct, huh? Not 3, sorry, yes, here how many alpha hydrogen, 3 alpha hydrogen. So this one, yes, 12 alpha hydrogen, and here it having only 6 alpha hydrogen. So this one is more stable. So more stable, so heat of hydrogenation will be less. Here number of pi bond 1, but here it having 2 pi bonds. So more pi bonds, so it will be heat of hydrogenation will be more. So 2 is greater than 1. Now here you can see, here it having only one pi bond, here 2 pi bond, here 2 pi bond. So more the pi bond, heat of hydrogenation will be more, means 2 and 3 is relatively more than 1. So 1 will be at last. Now in 2 and 3 you can see here due to conjugation it is more stable, so its heat of hydrogenation will be less. So 2, then 3, then 1. Clear? Similarly here also due to conjugation, here more number of pi bonds are there, correct now? Then after here 2 and here 1, but again we will not apply that rule. Why? Because here it is aromatic, so some are aromatic, some are non-aromatic, then we will not apply number of pi bonds. So here you can see that more number of that, here that this one is more stable, so due to that more stable, its heat of hydrogenation, here heat of hydrogenation is relatively less, correct now? Excuse me, so here you can see that here it having 3 pi bond, so here due to that conjugation it is more stable, so more stable, so its heat of hydrogenation will be relatively less as compared to here some conjugation is, here this is aromatic, here this is non-aromatic, so its stability is relatively less, so its heat of hydrogenation little bit more as compared to this one, it having only one pi bond. So we can say that first it will be 2, then after 3, and then after 1. Next, coming to the last question, you can see here that here it having how many alpha hydrogen, 2 alpha hydrogen, everyone having one pi bond, and none is aromatic, all are non-aromatic. So here 2 alpha hydrogen, here 6 alpha hydrogen, here 6 alpha hydrogen, here also 6 alpha hydrogen. So we can say that this one is the least stable. So if it is least stable, then its heat of hydrogenation will be more. So 1 is more. Now coming to 2, 3, 4, this all having 6 alpha hydrogen. So you know that here that electron is moving from hyperconjugation, high electron density, to low electron density. Here also electron is moving from high to low, means this electrons moving in this direction, here also electron waves are moving in this direction. So both waves are destructive because they are colliding with each other. Here also you can see this electron waves, high electron to low, and this one also high to low, colliding with each other. Whereas this electron wave moving in same direction, so it is constructive interference. So this electron wave is more, so here stability is more. So stability is more, then heat of hydrogenation will be less. So I can say that in this first is that, or like that you can apply, see heat of hydrogenation. So first one is that 2 alpha hydrogen, less stable, so heat of hydrogenation is more. Now in this you know that heat of hydrogenation is a syn addition. So syn addition is where more favorable, in 2 as compared to 3 and 4. So 2, and then after coming to 3 and 4, where syn addition is more favorable, in 4. So syn addition, so here 4, and then after 3. Now coming to heat of combustion. So heat of combustion, in that this one is destructive, interference happening, high to low electron density. This one also destructive, whereas this one is constructive. So due to that constructive interference, this compound is more stable. So if it is more stable, so its heat of combustion also will be relatively less. So here heat of combustion for fourth you can see relatively less. Why? Because if it is more stable means its ignition temperature will be more, means y minus x. So x value is more, so heat of combustion will be less. So fourth will be less. Now in 2 and 3, you can see that here this is destructive interference happening. Here also destructive interference happening. Along with that, here methyl group and methyl group repulsion. So cis is relatively unstable than trans. So this is unstable means its ignition temperature will be less, means heat of combustion will be more. So 1, then after 2, then after 3, 4 is already less due to its constructive interference. It's that hyperconjugation is more stabilized, means fourth is more stable. So its heat of combustion will be less. And heat of combustion only will tell the stability of this molecule. Why? Because heat of combustion is the complete factor. There we are burning this compound 100%, whereas heat of hydrogenation is the partial factor, where we are only adding hydrogen by breaking pi bond. So heat of combustion is more prominently and precisely accurately define a stability order, means more the heat of combustion, less will be stability. So here you can see heat of combustion of 1 is higher, so its stability is less. So 4 is more stable, 1 is less stable. So 4, 3, 2, 1. And here we completed each and every concepts with proper explanations. I tried my best for this synopsis. Along with that classes, whatever we studied, after that if you are revising this one, this will give you concept also, clarity also, confidence also. And here we completed GOC. Thank you very much.